Hi everyone. So today we're going to look at Activity 8.1. So if you haven't already done so, first read the scenario for Activity 8.1 and then also open up the data file. The data file is on the Google Drive for this class. Okay. All right, so the scenario we're going to look at today is a simple one where you have three groups and varying based on how much sleep they received. So they either got to sleep for 6 hours, 7 hours, or 8 hours. And what we're looking at is the amount of time they spend using social media. Okay. So we're going to work through this activity. I'm not literally going to walk through every question step by step, but I'm going to cover all the ideas in order that they are on the activity, so to help you as you answer the activity questions. Okay. All right, so first of all, why do we do an ANOVA here? Well, we're doing an ANOVA because we have three groups, right? 6, 7, and 8 hours, and people are randomly assigned to those three groups. And then our dependent measure is time using social media, which is measured on an interval ratio scale. Okay, so an ANOVA is an appropriate test here. Then we can look at the assumptions that need to be met for doing an ANOVA. Right? So one of those assumptions is normality. And that means that the distributions of sample means are normally distributed. Now, that assumption can be met in a couple of ways. One could be if we know that social media time is normally distributed in the population, we would know that the distribution of sample means are normally distributed. But if we don't know that, what we rely on is having a big sample size. So if you have a relatively large sample size, we know that the distribution of sample means is going to be normally distributed based on the central limit theorem. Okay. So if you look at your data file here, you can see that we have 60 people per group. So if you scroll through there, we have 60 people per group for 180 total, which means we have a reasonably large sample size and are pretty confident in that normality assumption. Now we also have the assumption of independence, which means that each person's data is independent of everybody else's data in the study there. Okay, and that's based on the methods of the study, making sure that you collect your data carefully. And then finally, we have homogeneity of variance, which we're going to come back to in just a moment. Okay. So what we're going to do here is do an ANOVA where we're going to test the null hypothesis here that all of the means for our three groups are really equivalent to each other. So let's start by actually looking at our means. Right? So we're going to do an ANOVA by clicking on ANOVA, the ANOVA menu, and then just selecting the first ANOVA there. And then we're going to look at sleep group as our fixed factor, where factor is an independent variable. And then I'm going to look at social media time as my dependent variable. Okay, so let's look at plots here. To get a plot, I'm going to move the sleep group over onto the horizontal axis, and it is putting points for the 6 hour, the 7 hour, and 8 hour group. Okay. You can also on your plot ask for error bars. And those error bars, if you click on the error bar, you can get standard errors, right, or confidence intervals. And either one is fine as long as you know what you're looking at. Right? And those are, and here I have it selected as confidence intervals. Right? But right now what we're looking at is the means, and see that the 6 hour group appears to have used social media more than the 7 hour group, which is also a little bit higher than the 8 hour group. Right? So just ballparking and getting a sense of your data to start with. Right? Noting here that our y-axis only goes from 220 to 320. It'd be better if that went from 0 to 320 because this sort of exaggerates the difference that we're looking at a bit. All right, so we know what our data look like starting off here. And let's go ahead and work on doing our ANOVA. Okay. So to do the ANOVA, just by the fact that we moved our variables over to the boxes on the left here, we got the ANOVA output. All right, so in our output, the variables or the values that we care most about are going to be the F and the P value ultimately, but you really need to know where that F and the P value come from. Okay? So an analysis of variance means you're going to analyze your variance and break it up into two parts. You're going to have variability between treatments, which is our sleep group. These are our treatments as the sleep group. And then we're also going to have within treatment variability, which is often called residual or error variability. So the sleep group variability is made up of the treatment as well as individual differences in air, whereas the residual variability is only made up of individual differences in air. Okay? So we would expect if our treatment has an effect on your dependent measure that our mean square for the treatment will be bigger than the residual. Right? So the way we can basically for the F, what we're doing is taking the ratio of the mean square between treatments and the mean square within treatments or residual. Okay. So the F is these two values, the mean square sleep and the mean square residual divided by each other. Okay. So we get an F of 5.847, right? And if in fact the null were true, right, and there was really no difference between the means, you would expect an F of about 1, right, because we're taking the ratio of between treatment to within treatment variability, and we would expect those two values to be about the same if the treatment doesn't work at all. We expect an F bigger than 1 if the treatment does have an effect. Okay? So we get an F of 5.85 and then computed a p-value. And the p-value is the probability that you would get an F of 5.85 or greater if in fact the null hypothesis is true. Right? So that p of 0.003 tells us that it's very unlikely that that mean difference is just due to sampling error. Okay, so that's really unlikely. Okay. The thing with the overall ANOVA is like, okay, now I know that all three of my means aren't equal to each other, but what I don't know is which ones are different, right? It's possible that only two of those means are different from each other, or all three of them are different, or two pairs of the means are different from each other. To figure that out, we're going to do post hoc tests. Okay? So to do the post hoc test, you click on the post hoc menu over here on the left-hand side, and you're going to move sleep group over into the box on the right to get post hoc tests. Okay? Also ask for the effect size associated with that post hoc test as well. That'll give us Cohen's d for each of those comparisons. Okay? All right. One other thing while we're doing this, click on additional options so that we can get descriptive statistics. We haven't gotten those yet. Okay. So the descriptive statistics box gives me the means and standard deviations for all three of our groups. Right? So we're getting the mean number of minutes people use social media in those three groups. Right? Now our post hoc tests are comparing those different means. Okay, so we're doing a comparison. The first post hoc test is a comparison of 6 to 7, right? The group 6 to group 7 had a difference of 29.924, right? That's the difference between 287.286 and 257.361 down here in the descriptives table. Okay? So it's computing the mean differences for all pairwise comparisons. It's comparing group 6 to group 7, then group 6 to group 8, and then group 7 to group 8. Okay? So note there's no 6 here on that second line, the gray one. You're just supposed to know that the 6 above it applies to the one below it as well. Okay. Okay, so for each of those mean differences then, it computes a t-test. Right? So the t-test is computed here, as well as an effect size associated with that t-test. Right? So we can see that the difference between 6 and 7 is a medium-ish effect, right? Small to medium. The difference between 6 and 8 is a little larger, right? Medium to large-ish. And then the difference between the group 7 and 8 is small, with an effect size of 0.19. Right? Now we also want p-values associated with these t-tests. Okay, so in order to get the p-values, we're doing in this class the Fisher LSD test. So the Fisher LSD test, unfortunately, you can't get the p-value for that in JASP. So you're going to have to get the p-value someplace else. So what you need to do is jot down those t statistics, right? So you have a t of 2.291, a t of 3.344, and then a t of 1.053. 3. Okay. And then we also need to know is the overall degrees of freedom here, which in this case is 177 is our degrees of freedom. And I'm getting that from the degrees of freedom with residual. So that 177 is our degrees of freedom. Okay. Okay. So our next step then is we're going to have to go to a web calculator to get the p-value for the Fisher LSD. It's just using a t-table, a regular t-table that's in no way corrected for anything. So I'm going to switch windows here to a p-value calculator. And there's links to these on the textbook website. I'm using graphpad.com right here. Okay. But my first t was 2.291, and the degrees of freedom was 177. So I can compute the p-value, and it tells me the two-tailed p-value was 0.0231. Okay. So the probability that I would get a t of 2.291, or a more extreme t, if the null is true, is 0.0231. Right? So it's very unlikely that that first comparison that we're observing between groups 6 and 7 is due to sampling error. Right? That difference is probably not due to sampling error. The next t we have is 3.344 with the same degrees of freedom. And here my p is 0.001. Right? Which again is very unlikely. It's telling me that the probability of getting a t of 3.344 or more extreme if the null is true is 0.001, which is really unlikely. Right? So that comparison between groups 6 and 8 is also unlikely to be due to sampling error. And then finally, my last t is 1.053, and that gives me a p of 0.29. So the probability I'd see that observed difference if the null is true is 0.29, which that's pretty likely. There's basically almost a third chance that that's the case. Okay. So let's go back to JASP. Okay. And so again, you're ignoring these two PPs. They're a little bit different than when you get with the Fisher P. You have to get the P someplace else. Okay. So our t for that first comparison was 2.291, and we got a p of 0.0231, right? So you have to have jotted those down someplace else, right? But basically what we now know is that group 6 and 7 are different. It's unlikely to be due to sampling error, and group 6 spent more time on social media than the group 7. Okay. We also know that group 6 spent more time on social media than group 8. But we also know that groups 7 and 8, the p-value was 0.29, pretty likely to be due to sampling error. So we're reserving judgment on this particular difference. There's a difference there, it's relatively small, and it's most likely due to sampling error. Okay. All right. Okay, so again, remember, in order to get the p-values, don't use the Tukey, but instead you're going to a website to get those p-values to get the Fisher LSD test. Okay. All right, so for each of those comparisons, we have our p-values. Now let's also take a look at not confidence intervals, but effect sizes. There are different effect sizes in your ANOVA. Right? So under additional options, click on Estimates of Effect Size and ask for partial eta squared and omega squared. Okay, and those will show up in your overall ANOVA summary table at the top. Right? Where our partial eta squared here is 0.062 and the omega squared is 0.051. Right? So these are both just overall estimates of the effect of sleep group on amount of social media. Right? That can be interpreted as a percent of the variability in social media time explained by which sleep group they're in. Right? We're going to be using omega squared. People argue it's a better estimate because eta squared, partial eta squared, overestimates the size of the effect. Right? So we have basically 5% of the variance in social media use explained by sleep group, right? Which is interesting, but what's more interesting usually is looking at the effect sizes, Cohen's d for the pairwise comparisons. Right? There's